In the past few videos, we've seen a few examples of functions that take complex numbers to complex numbers, and in this video I want to supply a third example. But the first two we've seen so far are what happens when you multiply the complex numbers by some fixed complex number re to the I theta. Alright, so that's a complex number written in polar coordinates. Here z is the variable, and you're just multiplying all of them by re to the I theta. And the other example of function we saw was conjugation. So now an important point is, since we can't really visualize four-dimensional space, we can't see the graphs of these functions. I mean, the graph of a function is the set of all points x, comma, f of x. If you think of just the graph of a real valued function or something, you'd plug in some value x, and then you'd look at the point x, comma, f of x. The y-coordinate would be the value of the function at that point x. So you need r and r for a real valued function. Each is one-dimensional, so this is overall two-dimensional, and we can visualize these graphs. For complex numbers, we would have to visualize the situation where x and f of x are both complex numbers, elements of C. So we'd need a two-dimensional space to show all of that. And if we're going to put two-dimensional spaces kind of at right angles with each other, you need to be thinking of a four-dimensional space, which we can't visualize. But that doesn't mean we can't visualize complex functions at all. There are some ways of doing it. For example, if you look in Needham's book called Visual Complex Analysis, he has lots of pretty pictures where he plots these functions in three-dimensional space, where the x and y axes form the domain, the complex number domain, and the z-axis does not denote the value of the function necessarily, because that's a complex number. You'd need more than just one axis to do it, but it does give you the modulus, or the length of it. So look at this book and see the pictures in there. That's one way of visualizing it. I think the most natural way of visualizing it is to just imagine them as transformations of the complex plane, transforming the complex plane. So that means that you kind of visualize the domain and the range as being the same thing, and you just imagine how that map is kind of altering or manipulating it. So, for example, multiplying by a fixed number re to the I theta. So we discussed before that this has the effect of rotating by an angle of theta and then scaling by this factor of r. So I've drawn the picture right here. You imagine this entire plane being rotated by theta and then stretched by r. I've shown you what happens to one point here. Z, this point, you rotate it by theta, it goes here, and then you stretch it by a factor of r, and then it moves over there. But you should kind of visualize this happening to the entire plane, if you can see this. Imagine taking this entire thing and rotating it all by an angle of theta. Just rotate the entire plane around the origin by an angle of theta. And then stretch it. Just take everything and just kind of imagine grabbing both ends of the plane with your hand and just stretching it out. That's what you should be visualizing when you see this. And then conjugation, you map z to z bar, and remember that it preserves the real component, but it negates the imaginary component. So x plus iy, if that's what z is, then that gets mapped to x minus iy. The x stays the same, the y changes. So yeah, the real part of your complex number stays the same, and the imaginary part gets negated. And that has the effect of reflecting about the real axis, right? Because the real component is basically just the x-coordinate. So since that stays the same, z bar should have the same x-coordinate as that, except the y-coordinate is the imaginary part. So when you negate the imaginary part, you're really negating the y-coordinate. So it reflects it over here. Negative the imaginary part of z is the imaginary part of z bar. And so, they have the opposite angle and so on. We'll talk about that a bit more later on in the video. But that's the picture. Just imagine taking everything here and just kind of reflecting it so that down here there's like this mirror right here at the x-axis. And in particular, that means that the real numbers are fixed, right? So if you have like -3 here, what's the conjugate of -3 thought of as a complex number? Well, it doesn't have any imaginary component. Its imaginary component is 0, so that's just -3. Or if you like, you can think of it as -3 plus 0i if you want to bring that out. and then the conjugate of that is negative 3, that stays the same, minus 0i. But of course, adding 0i and subtracting 0i don't make a difference. It's the same thing. So those are the two pictures. We have this kind of reflection around the x-axis, or the real axis, and we have this rotation together with a stretching. And remember that if r is equal to 1, there's really no stretching, so it's just a rotation. And if theta is equal to 0, there's no rotation, it's just a stretch. So these kind of stretch/rotates in particular include stretches by themselves and rotations by themselves. So now we're going to discuss what I think is a more interesting example of a function from the complex numbers to the complex numbers called inversion in the unit circle. And it's given by this formula here. What do you do to the complex number? You conjugate it and then you invert it. You put 1 over it. Or vice versa, you can invert then conjugate it. It really doesn't matter which order you do this in. I mean, since the conjugate of 1 is equal to 1, 1 is real for the same reason here for the negative 3. And conjugation, remember, obeys this property that zw bar is equal to z bar times w bar. So that proves that inverting then conjugating is the same as conjugating then inverting. Well, I mean, okay, the way I've written it here, I've conjugated first and then I've inverted, right? But what if I had first inverted and then I conjugated? Well, because conjugation breaks up over multiplication and division is just an example of multiplication, this is the same as 1 bar over z bar. That's using this property. And then you say, well, 1 bar is the same as 1, right? Because 1's a real number. So that's just equal to 1 over z bar. So there you go. It doesn't matter what order you do it in. But do notice that this really is only defined when z is not equal to 0. You can't divide by 0. So f is not a function from the complex numbers to itself per se. It's a function from the non-zero complex numbers to the non-zero complex numbers. And remember, this is my notation for non-zero complex numbers. So I think I first did that in the video on, remember, it starts with an N. I first did that on the video GL1C or something when I was explaining that. Okay, so now we know what conjugation does. I just talked and reviewed that. It flips things over the real axis. But what does the inversion by itself, z to 1 over z, do? That's the question. Because inversion in the unit circle, as I've defined it, involves both. It's a composition. First you invert, then you conjugate, or vice versa. So we know what conjugation does. Let's handle the inversion by itself. What does this map z going to 1 over z actually do? Alright, so let's write things in polar coordinates and get an idea of what happens to the geometry of it. That's usually very helpful with these sorts of things. So if we write z as re to the I theta, then 1 over z, which is the same as taking z to the negative first power, is equal to re to the I theta to the negative first power. This power distributes. You get r to the negative 1, e to the I theta to the negative 1. Of course, power to a power, you just multiply the powers. So that's r to the negative 1, e to the negative I theta. So, okay, we've written it in polar coordinates. We've written 1 over z in traditional complex polar coordinates. Something times e to the I something. So it's that something, that first something is 1 over r, that thing on the outside. That's the length of it, or the modulus of it. And the angle is whatever you're multiplying by I in the exponent of e. And that's negative theta. We're multiplying I by negative theta. Alright, so that's our angle. That's our argument here. So 1 over z does what? It inverts the length and it negates the angle. So let's draw some pictures of what this sort of thing is going to look like. Okay. So if the original length r was 1, so here if z was just of the form e to the I theta, which would put it on the unit circle, r would equal 1, it would have length 1, then the new length would be 1 over r, that's what we have here, but 1 over 1 is just 1. So it too would be on the unit circle. So the unit circle gets mapped to the unit circle, but the angle still gets negated. So on the unit circle, this reflects things about the x-axis, right? So if you had something on the unit circle right here, and let's say it's at an angle of theta, well, the length gets inverted, but that doesn't change, but that theta becomes negative theta. So what ends up happening is it mapped this point on the unit circle to this point on the unit circle. Of course, if the angle theta was 0 or pi, then theta would equal negative theta in that case. So these 2 points are fixed. So kind of, as long as you're restricted to the unit circle, it acts like conjugation almost. It reflects things around this real axis. This point gets mapped to this point, and this point gets mapped to that point, and so on. But what happens if r is greater than 1? Switch to blue here. If r is greater than 1, then 1 over r is going to be less than 1, right? Like 2 is bigger than 1, 1/2 is less than 1. So things outside the circle, right? Having r greater than 1 in the first place means that you're outside the circle, the unit circle. Go to things inside the circle, because 1 over r, the new length, is going to be less than 1. So for example, if you draw this point over here, then when you invert, what's going to happen is your new length is going to put you somewhere around here. That was a length of r. This is the length 1 over r. It's going to be a little less than 1. But of course, on top of that, theta gets negated in the same way, so it also involves a reflection here. So that point gets mapped to some point like right there. Okay. The length is 1 over the reciprocal of the length, and the angle gets negated. Right. So that angle becomes negative that angle. Okay, and finally, if r was originally less than 1, then things swap again. That means that 1 over r is going to be greater than 1. So things inside the circle are going to get mapped to things outside the circle. So for example, this point here, again, angles are always going to get inverted here. So it's going to be a reflection. Things below the real axis go to things above it and vice versa. But it's not this length. It's going to be a length slightly bigger than 1. So it's going to get mapped there. So this point is going to get mapped to like that point right there. Okay. So notice that in each case, the angle really is negated. There's this extra reflection through the real axis, which is kind of annoying, right? So one way we can get rid of that is to conjugate. So that's why we conjugate, to undo this extra reflection. Because that's exactly what conjugation does. It reflects back. And if you reflect twice, then you've undone the reflection. So in symbols, here's what it looks like. If you're just conjugating r e to the I theta, so we're looking at how conjugation looks in polar coordinates, then that's the conjugation of, and here I'm just using Euler's theorem or Euler's formula to break r e to the I theta into r cos theta plus r sin theta times I. And it's the conjugate of that. But of course, this is our real component. This is our imaginary component. So this stays the same. This gets negated. And that's what we have here. R cos theta matches here. Except now we have a negative r sin theta I instead of a plus r sin theta I. And that's the same as r cos negative theta plus r sin negative theta times I. In other words, we can take this minus sign here and put it inside with that theta, because sine of theta is an odd function, if you remember that language from calculus. It's a function where if you negate the variable, it's the same as negating the function. That means that it's kind of symmetric if you reflect around the y-axis and then the x-axis or something in terms of real variables. And cosine of negative theta is just cos of theta. It's an even function. So there's no harm in putting a minus sign there. It's just going to disappear in cosine of theta. Okay, so that's the same as, well, r cos theta plus r sin theta, r cos negative theta plus r sin negative theta is equal to r e to the negative I theta. Again, we're applying Euler's theorem. This time the argument is negative theta instead of theta. Alright, so what have we seen? The conjugate of r e to the I theta is r e to the negative I theta. So the length is unchanged, r stays the same, but theta gets negated, the angle gets negated. Right? So that's what causes that reflection around the real axis. It's another way of seeing it. And of course, as we've seen before, if you invert it, just recalling what happens up there, if you invert it, you're inverting the length, and you're also negating the angle. So if you do both of these things, you invert and you conjugate, then what's going to happen? You're going to negate the angle twice, right? The angle gets negated in both cases. It gets multiplied by -1 twice. So that means that it ends up staying the same. It's unchanged. But the length only got inverted once, here when you did the actual inversion. Length stays the same under conjugation. So I think I'm beating a dead horse here, but the point is that by the end of it, the formula for inversion is re to the I theta, inversion in a unit circle, gets sent to, well, if z gets sent to 1 over z bar, both of them happening at the same time, then this gets mapped to, well, the inversion causes it to turn into 1 over r e to the negative I theta, but then the conjugation negates the angle again. It becomes negative I theta. Or if you like, I can write it like this. First we invert from z to 1 over z, and that puts us as negative I theta, and then we do something else. Then we conjugate. So conjugating puts it at 1 over z bar, and here it negates the angle, so it preserves 1 over r, but it takes us back to 1 over e to the I theta. So the overall equation for 1 over z bar, what does that equal? It sends r e to the I theta to 1 over r e to the I theta. It inverts the length, but it doesn't do that annoying flip with the angle that we had before with just regular old inversion. So let's just draw a picture of what that would look like. Now, outside the circle still means outside the circle, except now the angle is preserved. So outside turns into inside, but the angle is the same now. I don't have to do some weird little reflection here. This point gets mapped to this point. And also, think about it vice versa. This point inside also gets mapped to that specific point outside. Because if you repeat this map twice, 1 over z bar, and then you invert and conjugate again 1 over that whole thing bar, what does that equal? So this bar here is just conjugation. Well, you're conjugating 1 over z bar, means you're conjugating 1 and you're conjugating z bar. That just kind of undoes the conjugation. So it's 1 over z. But 1 over z flips the z back up, and that's just equal to z. So what I've seen is that if we apply this map twice, this map f, which is 1 over z bar, if we apply it twice, you get back to where you started. So it swaps these things. It's kind of like a reflection through the unit circle. In the same way that a reflection fixes an axis and then it swaps either side of it, well, that's the same thing that's going on here. We fix the circle and we swap the inside with the outside. And remember, we don't have to worry about what's going on at the origin because that's not part of the discussion. We've thrown out the origin in this conversation. So just some more examples. Again, you're inside here, you go outside, you're on the circle. Now, you're not reflecting anymore. Remember, we undid the reflection, so now every point on the circle really is fixed. So that's what justifies thinking of it as a mirror, And finally, one important point, the further you get away from the unit circle, if you just kind of have a sequence of points going further and further away, when you invert it, you're going to get something which gets closer and closer to the origin. In a sense, you can think of 1 over 0 as kind of being equal to infinity. It kind of maps it to infinity. And there's a way of making this kind of rigorous if you imagine the sphere instead of the plane, but that's something we're not going to discuss right now. But the point is, as you go away from the circle, you're going away from the circle towards the center on the inside. And vice versa. I mean, if you go towards the circle, then you're approaching the circle here. So the point is that things that are really close to the circle still stay close to the circle. They just swapped sides, This point gets mapped here, and the further away you are, the further away you get from the circle, and so on. So that's kind of developing the intuition of what inversion in the circle actually looks like. So notice we're just going to look at some other formulas here. Notice that z times 1 over z bar, so we've applied the function, we actually multiply it by z, is the same as z over z bar. Okay, that's just algebra. And then if we multiply both sides by, both the top and the bottom by z over z, or multiply them both by z, right? This is just 1, so it's okay to multiply by 1. And z is not 0, so we don't have to worry about dividing by 0. Then this is just z squared over the norm of z squared. Okay, if you cancel this z with one of the z's up here, what do you get? Cancel this with one of that. You get that 1 over z bar is actually equal to z over the norm of z squared. Okay, so you're scaling z. This is a real number. You're multiplying by a real number. And that's the factor with which you're scaling. That factor is basically saying re to the I theta gets sent to re to the I theta, and then you have to scale by dividing everything by the square of your norm, r squared. And that'll turn you into 1 over re to the I theta, which is the formula we got earlier. But but this is just another formula that you might see for it. And if we look at how this all looks when we write it out in these Cartesian coordinates, real and imaginary coordinates, z equal to x plus iy this makes the z bar equal to x minus iy, so that 1 over z bar is 1 over x minus iy. And if we multiply both sides by the original z, x plus iy, that has the effect of realizing the denominator. X minus iy times x plus iy is x squared plus y squared. And we have an x plus iy times 1 on top, so that's just x plus iy. And you'll notice this is the exact same formula we had before. X squared plus y squared is the norm of z squared, and x plus iy is z. So this is just the same formula written in these coordinates. But you might also break it up now, distribute it, break up the numerator, and it ends up looking like this. So that's a nice, pretty formula too. And in particular, this formula tells you what the real component of it is and what the imaginary component of it is. Okay.